Hi all, quick lesson on electrical power. Um, this can be found, you're not supposed to lick your fingers, coronavirus time. Um, yeah, sorry. This can be found in chapter 17 on page 580. So the original definition of power from chapter 5 was that power is the rate at which work is done, or work over time, measured in watts, or the rate at which energy is used, because work produces a change in energy. All right. So power is still defined as the rate at which work is done, or the rate at which energy is used or transferred. All right. So delta E over T, or work over T. For electricity, I'm not going to go through the proof, but that can eventually come down to current times voltage. All right, current times voltage. Remember that power is the rate at which energy is transferred or used, and so that's going to be in joules per second, which is a watt. Remember, in combination with Ohm's law, we can rewrite this depending on what we're looking for. I can put IR in for delta V. So P equals I times IR, which is I squared R. And if you look on page 580 and 581, and I highly encourage you to do that in the textbook, they talk about I squared R losses. So when current passes through a resistor, and it's the current that really matters, because the current is the flow of charges, and heat is generated when the charges collide. So power is proportional to the current squared. Um, so if you had twice the current, you'll have 4 times the power. And if you don't want to lose energy, then that's 4 times the power loss, like an energy transmission between like Hoover Dam and Los Angeles. And those are sometimes referred to as I squared R losses. That's when you lose energy in transmission. That's like the heating up of your battery. Okay, this is sometimes referred to as Joule's law. Uh, you could also solve for I and put so I equals delta V all over R, and put that in for current. So P equals delta V over R times delta V, which is delta V squared over R. Okay, so the ones that I use the most, that one and that one, but that one, it can come in handy also. So one of the reasons why you have transformers. Now, these are written for ohmic devices like a resistor. They're really not meant for light bulbs, which are non-ohmic, but they still can use. We can still use it as an approximation. Okay, even with non-ohmic devices like a light bulb. And just to get an idea, when power is produced at a generating station, such as Palo Verde, it's transmitted at extremely high voltages. And by the way, have you ever wondered why it is that, say this is at 10,000 volts, and a birdie lands on the power line? So this is a power line. It's at 10,000 volts, and a bird lands on that power line and doesn't get electrocuted. Well, if you think about it, if this point is at 10,000 volts, and this point is at 10,000 volts where the bird's feet land, all right, they're right next to each other. They're both at 10,000 volts. And so how much current is going to pass through the bird, all right, if this is at 10,000 volts and that's 10,000 volts? Well, there's no delta V, because 10,000 minus 10,000 is 0. And so there's no delta V, and if there's no delta V, there's no current flow. That's why a bird can land on a high voltage line and not get shocked. If you were skydiving and you landed and you touched high voltage line by accident, that would be you would get an initial shock. It would be very shocking, but and then you decide, oh, I see a ladder over there. You're dangling in the air, and you see a ladder over there. You start going over. Oh, I'm going to move over and grab the ladder and climb down the ladder. Be careful, because you're at 10,000 volts. Again, you might get an initial shock because you were initially neutral, but you'll fill up to 10,000 volts real fast, and then you can hold on. You might, but still, now you're at the same potential as the wire. But now you make your way over there, and if you grabbed on, don't do this. If you grabbed onto the ladder, which is grounded, suddenly there's a potential difference. 10,000 volts. Beforehand, when you're holding on with both hands is backwards. The camera. Anyhow, 10,000, 10,000, the difference is 0. Then you grab onto the ladder, and now that's 10,000 and 0. That's bad. Okay. So, anyhow. We transmit electricity at high voltages so that at high voltages, the current is small and the voltage is large, because again, it's the current, it's the collision of charges with atoms or molecules that generates heat. So it will generate at a high voltage. And then you get into the neighborhoods where they're going to use the electricity, and we have what's called a step-down transformer, and we step down the voltage, and that steps up the current. So we can, you still get the same power. In America, we have chosen to use a slightly lower voltage, around 120 or so volts. Again, this is alternating current, not direct current, but it's still similar. We use 120 volts. And so we have a slightly higher current than in Europe, where they have around 220, 240 volts, right in that range. And so they have a higher voltage, and so they have a lower current. The higher voltage can lead to a higher, there are trade-offs in terms of higher potential, could be a higher chance for spark and stuff like this. But it's a lower current. So there are definitely trade-offs there. What last thing I want to say here, so you've got some homework that deals with this. And one question, by the way, on page 588 says high voltage, question 34, high voltage transmission line with a resistance of 0.31 ohms per kilometer, and that carries it through these transmission lines for 160 kilometers. So you can calculate the resistance just by multiplying that out. The current is 1,000 amps, and the line has a potential of 700 kilovolts. You should work in volts, all right, not kilovolts. But, what is the power loss? So you can just use I squared R for that, your I squared R losses. That's the power loss during transmission. What is the fraction of the power transmitted? The fraction of the transmitted power, what fraction of the transmitted power does the loss represent? And so you can calculate I squared R for the losses, the current squared times the resistance that you get from the data in the problem. And then you can also calculate the power available, which is that same current times just times the potential. Don't do a delta V. In that case, the power available is just going to be current times the available voltage, okay? When you do delta V, it's power used, as opposed to IV is power available, okay, in that question. Lastly, we've talked many moons ago that said that the joule is a really small unit. So when you look at your electric bill, hi Bill, Bill, hi Bill, Bill. So a watt, no, excuse me, your electric bill is in kilowatt hours. And remember that That's abbreviated kW and then H. Remember that power is I times V. It's also energy over time. So I could say that energy is equal to power times time. I just multiplied time to the other side. And so this is an energy unit. Power in kilowatts, thousands of watts, that's 1,000 joules per second, times time in seconds. So kilowatt hours in this case, the unit here is kilowatt power hours. Well, how many joules is that? Well, let me see here. A kilowatt, again, is 1,000 watts, which is 1,000 joules per second. Kilo, 1,000. And an hour is 3,600 seconds. All right. And so that's 1,000 times 3,600, which is 3.6 million joules. So 1 kilowatt hour is 3.6 million joules. And this is the energy unit that the power companies use. And you might be charged, for example, I'm making this up, 10 cents per kilowatt hour. You could calculate, there's a question in there, you could calculate how much power you use, convert it to kilowatt hours in terms of energy. So you turn on a light bulb and leave it on for a certain amount of time. You can calculate the energy that it uses, be in kilowatts. So calculate the amount of energy it uses, and then convert that to kilowatt hours. And if it's 10 cents per kilowatt hour, you just multiply it by 0.1, because $0.1 is 10 cents. And you can solve that kind of problem. Anyhow, so you do have some homework on here. It's on Canvas. It's I think it's questions. I'm not looking at the homework, but I think it's questions 31 through 34 on page 589. Okay. God bless you all. I sure miss you. The classroom. I'm in the classroom today. Might be the last time for a while. And there's the classroom. Hi. Take care of yourselves. God bless.